Hello everyone, so today we're going to be looking at factorial Diophantines, and we have seen a couple of problems like this before, and really they keep coming up a lot, and especially if you go over some of the AOPS platforms or other math forums, you'll see that these are one of the most common types of number theory, one of the most common types of Diophantine equations that you'll see, factorial Diophantines. And really, whenever you see a factorial Diophantine, it's 99.99% of the case you just have to reduce mod n and figure out the modular residues. So effectively, the problem kind of reduces to finding out what value of n you have to reduce it to. What mod n, mod 5, mod 6, mod 7, what exactly do you have to go? And again, the idea of that really depends upon experience. So the more experienced you are, the better you get at it, figuring out what exactly mod n you need to use. So let's see how we can figure out this problem. And this is the problem number 4 from the United States of America team selection test for the IMO in 2017.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
In this video, we're going to be looking at factorial Diophantines, reducing mod n, modular residues, residue classes, the complete residue system, some fancy terms, but really they're all more or less the same thing. And the concept is relatively not that hard to grasp. Then we have certain book sessions for senior math Olympiads, and at the end, a similar but charging problem. So we need to find all non-negative solutions to this equation, 2 raised to the power a plus 3 raised to the power b plus 5 raised to the power c equal n factorial. Now again, whenever you have certain types of questions like these, either it will have like a family of infinite solutions or just a small number of solutions. And like I've said many times before, the factorial notation and the exponential notation, so let's say a raised to the power x, they don't really gel well with one another. So there's most likely only going to be a certain set of values, some finite values of a comma b comma c and n for which this equation is satisfied, and that's what we need to find essentially. So whenever you see a factorial Diophantine, whenever you see a factorial on one side, really only a couple of ideas can be involved and the most important is working mod n, modular residues, and kind of bounding. So by bounding, I mean like find out a certain value of n. For example, for n is greater, let's say n is equal to greater than or equal to 5, there exists no solutions, and try to prove that. For n is equal to greater than or equal to 7, there exists no solution, try to prove that. I'm mostly giving an example, it's not applicable to this problem specifically. But yeah, the kind of idea is that's kind of the algorithm that you need to follow. It's very algorithmic actually, it's very algorithmic. And you just need to find out what value of n exactly you need to reduce it. So let's see how we can deal with this problem. So first thing is maybe we can form an inequality over here. 2 raised to the power a plus 3 raised to the power b plus 5 raised to the power c is going to be greater than or equal to 3 raised to the power 0 plus 3 raised to the power 0 plus 5 raised to the power 0, because these are non-negative solutions. 0 is obviously non-negative number. It's neither negative, neither positive. So this quantity on the left hand side is going to be at least 3, right? It's going to be at least 3. So what we can say that n is equal to 1 and n is equal to 2 can never be solutions. So n has to be greater than or equal to 3, right? That's, I think, fairly trivial. Because if n is 1 and 2, then the right hand side will be 1 and 2 respectively, 1 factorial, 2 factorial, which is 1 and 2, but the left hand side will always be greater than or equal to 3, so they'll never be equal. So let's first consider the first case 1, where n is equal to 3. So I'll get 2 raised to the power a plus 3 raised to the power b plus 5 raised to the power c is equal to 3 factorial. In other words, 2 raised to the power a plus 3 raised to the power b plus 5 raised to the power c is equal to 6. And well, one of the solutions that you can form over here is 2 squared plus 3 raised to the power 0 plus 3 raised to the power 0 is equal to 6. So 2, 0, 0, 3 is a solution. And another thing that you might form over here is 2 raised to the power 1 plus 3 raised to the power 1 plus 5 raised to the power 0 is also equal to 6. So 1, 1, 0, 3 is also a solution. So you get 2 solutions for this case. And yeah, these are the only 2 values that you can essentially find. So now we move on to case 2. And you can really play around with this. There's actually another very interesting thing that you can actually see. Now, what was given the question? 2 raised to the power a plus 3 raised to the power b plus 5 raised to the power c is equal to 6, right? For this case. Now, a can either be 0, 1, 2, right? It cannot be 3, because then this would be 8 and you would have negative terms, which is obviously not possible in an exponential function. So a can be either 0, 1 or 2, and we really can see that a is equal to 0 has no solutions, because 3 raised to the power b plus 5 raised to the power c is equal to 5. This is obviously not going to have any solution. So a can only be 1 and 2. So 1 and 2 are the only 2 possibilities, and we have taken the solutions for both of them. Right, so effectively these are the only two solutions to this. Right, so moving on to case 2. So this illustration is essentially to confirm any doubts that may be left in your mind that there may exist certain other solutions for this. They don't, okay? They don't. So case number 2, we're going to consider n is equal to 4. So 2 raised power a plus 3 raised power b plus 5 raised power c is 4 factorial. Right, so 2 raised power a plus 3 raised power b plus 5 raised power c is 24. And there are a few ways to form this out. What I can see is 2 raised power 4 plus 3 raised power 1 plus 3 raised power 1 is 24. So 4 comma 1 comma 1 comma 4 is the solution. And yeah, this is in fact the only solution. Again, over here, the idea that you can use that a can be 0, 1, 2, 3 and 4. If check for a is equal to 4, and you can actually check that a is equal to 0, 1, 2, 3 do not work. None of these 3 work. None of these 4 work, and you can actually just check them case by case. And actually see that there exists no solution for this. So 4, 1, 1, 4 is the only solution for this case. So till now, we actually have how many? 3 solutions till now. Right? This is one solution, and we found 2 solutions above. Right? So 3 solutions till now. Now let's move on to case number 3. Case number 3 is I'm going to consider all n which are greater than or equal to 5. So this is where the bounding occurs. And then I'm going to make a claim. Let's make the claim that there are no solutions for n greater than or equal to 5. This is essentially the claim or the kind of bounding idea that I was telling you. There will only exist solutions for certain values of n. Right? So if n is greater than or equal to 5, this essentially implies that n factorial is congruent to 0 mod 120. Right? So because essentially any n greater than, for example, if let's say we have 6, right? So 6 factorial can be written as 6 into 5 factorial, which is obviously 0 mod 5 factorial, so 0 mod 120. This is kind of a standard observation. Again, now we're going to see the concept of modular residues, right? So again, modular residues, we can just compare the modular residue of 5 raised to the power x. We just make it like a table, 5 raised to the power x mod 120, I'm sorry. And then we compare it with 5 raised to the power x mod 20. And whatever we get over here is the modular residue, right? So if I put 0, I'll get 1. If I put 1, 5 raised to the power 1 mod 120 is 5. If I put 2, I'll get 25 mod 120, which is 25. If I put 3, I'll get 125 mod 120, which is 5. So 5 raised to the power x is essentially only 1, 5 and 25 mod 120. So this is the residue class of 5 raised to the power x mod 120. It's also called as congruent, it's also called as modular residue or residue mod n. Just certain names for it. So yeah, this is essentially the concept behind all of this modular residue and whatever terms that we were using. So yeah, 5 raised to the power x can be this mod 120. Now similarly, you can actually see that 2 raised to the power x will actually be 1, 2, 4, 8, 16, 32 and 64 mod 120. So this is the residue class for 2 raised to the power x. And similarly, let's formulate the residue class for 3 raised to the power x. We'll get 1, 3, 9, 27, 81 mod 120. So this is the residue class for 3 raised to the power x. So these are essentially residue classes, right? Residue classes for whatever 3 raised to the power x mod 120, 2 raised to the power x mod 120, and 5 raised to the power x mod 120. Okay, so well, they had given us, right, the 2 raised to the power a plus 3 raised to the power b plus 5 raised to the power c is n factorial. And if you're considering n greater than or equal to 5, so that essentially means that 2 raised to the power a plus 3 raised to the power b plus 5 raised to the power c needs to be congruent to 0 mod 120, which is what we have worked with in the question. Right? So essentially, if I just label this set as a, and if I just label this set as b, if I just label this set as c, the residue class, the elements in the residue class is c, if I just label that as c, I'll essentially get a plus b plus c is equal to 0. In other words, a plus c needs to be congruent to negative b mod 120, right? And well, you could have just seen if a plus b plus c for any values, is it ever equal to 0 mod 120, and it's not. And what I'm doing right now is just in a way simplifying it a little bit so that we can kind of like formulate it a little bit easily, right? So a plus c is congruent to negative b mod 120, and b was essentially this, right? So a plus c is congruent to negative 1, negative 2, negative 4, negative 8, negative 16, negative 32 and negative 64 mod 120, right? So essentially a plus c comes out to be 118, 116, 112, 104, 88 and 56 mod 120. So a plus c can be either these values mod 120, and what was a? A was essentially 1, 5, 25 mod 120, and c was what was c? 1, 3, 9, 27, 81 mod 120. And if you actually see the sum of these two, any two elements in this, and sum of any to AI plus Cj will never be equal to any of these. Let's consider this as x will never be equal to, let's say, xz mod 120, right? Where these are the ith, jth, and the zth elements, right? So any two elements, the sum of any two elements over here will never be equal to any of these elements over here. So therefore we have no solutions for n greater than equal to 5. And really you can have easily seen this as a plus b plus c is congruent to 0 mod 120, and here you can have directly stated that there exists no solution for this by just checking it case by case. Take any element from a, add element from b, and add any element from c, and just I'm gonna figure out all possible combinations. And then you can see that you really see that after a certain point none of these will ever be equal to 0 mod 120. It will never happen. They'll never be of the form 120k. That will never ever happen, right? And therefore there exists no solution of n greater than equal to 5. What I essentially did here was just simplify the casework, simplify some calculations for you a little bit. So yeah, we have only 3 solutions which we had formed earlier, which is 4, 1, 1, 4, 2, 0, 0, 3, and 1, 1, 0, 3, and that's all the solutions. So yeah, there was a team selection test problem from the USA for the International Math Olympiad, and it was a really nice problem. Essentially the same idea as when you receive factorial diophantine, you just have to work mod n. You just need to figure out what value of n you need to take, but other than that it's essentially the same thing. Work a little bit on the residue classes and you should be able to solve problems of these types. There are certain book sessions for senior math Olympiads. Principles and Techniques in Combinatorics, that's a great book. I Am a Compendium, Functional Equations, How to Solve Them by Christopher G. Small, Problem Solving Strategies by Arthur Rangel, Problems in Plane Geometry by Sharigan, and Elementary Number Theory by Sierpinski. And at the end we have a similar but challenging problem, and this is kind of like a similar version of the problem that we just solved. Find all non-negative solutions to 7 raised to the power a plus 4 raised to the power b plus 11 raised to the power c is n factorial. Again, whenever you see a factorial diophantine, you just need to work mod n. Just you need to figure out what value of n you need to use. And once you've done that, try to use the case of bounding. Take some value of n greater than equal to k, and then prove that there exists no solution for this k. Or maybe even like n, yeah, just take n greater than equal to k, and let's try to prove if there exist any solutions for this. I just try to, in most cases, you'll be disproving it. Like there will be no solutions greater than this, right? In most cases, that's kind of the idea of the bounding that we've used in the problem illustrated above. So yeah, if you're able to solve it or make any progress on it, let me know in the comment section below. And until then, I'll see you in the next video. Thank you very much and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.